Alright, folks, welcome back. I had another request to come in. They said they really understood A and B, they just really need help on C. But I'm going to go ahead, just for the better benefit of everyone, go ahead and work parts A, B, and C. Alright, so let's go ahead and get started with this problem. They want us to calculate the energy in joules of a single photon that has the wavelength of 5.00 times 10 to the fourth nanometers, infrared region, and do the same thing for a photon of wavelength of 52 nanometers of ultraviolet region. Then all of a sudden we got to calculate the maximum kinetic energy of an electron ejected by the photon in part B from a metal with a binding energy of 3.7 electronic volts. So, a lot going on here. The first two problems, A and B, are worked identically the same, so not too much difficulty. But part C, we're going to have to put forth a little bit of an effort, but still nothing too horrible. All right, let's go ahead and get started. All right, problem A. First thing that we need to do is make sure we know which formulas are going to be used on this problem. Alright, first of all, they want us to calculate the energy. In order for us to calculate the energy of a single photon, we need to use Planck's constant times V. And if you remember, that V is our frequency. So we've got to calculate the frequency in order to use the Planck's constant to get the amount of energy in a photon. Problem is, they've given us wavelength here, so we're going to have to use the another equation, which is the speed of light equation, which is C equals lambda times V. So once again, we're going to be solving for V, and then once we get this solved for V, we're going to plug it back into this equation. Okay, that, or you can make a quick substitution and just do it all at once. For example, what you could do is you could just take this V, solve for V. Algebraically, you would get V equals C divided by lambda. And what you can do then is you could actually take this portion and substitute it in for V. Okay, that actually looks like the easiest thing to do. That way we don't have too many problems going on. We could just do it all in one step. So let's just go ahead and knock this out. Alright, the energy of a photon then is going to be calculated using our modified equation of Planck's constant times C over lambda. Now that's in place of the V here, okay? Because we proved V is equal to C divided by lambda. Okay, so I'm just going to extend this fraction bar out to put the H on top with the C. So we're going to substitute those in now. Planck's constant is 6.626 times 10 to the negative 34 joules times a second. So we'll write that here, joules times a second. And that's our first number. Now in some books they have this as 6.63 times 10 to the negative 34 joules times a second, and that's okay. I'm not going to argue with that, but I've always used 6.626 times 10 to the negative 34 joules times a second, so I'm just going to keep using it. The speed of light is 3.00 times 10 to the 8th meters per second, and then all this will be divided by my wavelength, and the wavelength they gave us was 5.00 times 10 to the fourth nanometers Oops, that's an ugly N. Nanometers. Now, once again, if you remember from the earlier video and the earlier videos, nano is times 10 to the -9. So I'm going to make a substitution here as well on the nanometer. I'm going to change it to times 10 to the -9. So we're going to have something that looks really ugly. And I'm sorry, but like I said, I'm lazy. I like doing things all at once. Times 10 to the -9. And that is our nanometers. So there's M there. Now remember, this part right here is the nanometer part. Okay, so this part right here is still the original wavelength number, the 5.00 times 10 to the 4th nanometers. So there's the NO for the times 10 to the -9, and there's the M. I know it's not written correctly in scientific notation, but that's okay. It's only being used as a computational number, meaning it's not a final answer. So it would be fine to express it that way. Alright, let's go ahead and punch this into our calculator. So the energy of this photon is going to equal, let's punch it into a cheetalator. Oh, alright, there we go. Open parentheses, 6.626 times 10 to the -34 times 3.00 times 10 to the 8th, close my parentheses, divided by parentheses 5.00 times 10 to the 4th times 10, whoop, I got 2 times there, times, let's see, times 10 to the -9, and that's it. So close my parentheses. Now let's make sure it looks right. 6.626 times 10 to the -4th times 3.00 times 10 to the 8th divided by all this 5.00 times 10 to the 4th times 10 to the -9th equals, and I get the following answer for A. I get 3.9. I need 3 sig figs because of 5.00, so 3.98. So let me write that down. 3.98 times 10 to the -21. Now what is our units here? I know it's energy, so it's going to be joules, but let's prove that it's joules. Notice that meters cancels out meters, seconds will cancel out this seconds, leaving us with just joules. So that's why we know it's joules. Okay, so here's our answer for problem A. Okay, so problem A is completed. Yay! Okay, now the same principles are going to apply when we do problem B. I'm going to do the same process. I'm going to use the same formulas and everything. So here, since we're given another wavelength, we know to use the modified equation of the energy of a photon. So E photon equals, since we're given the wavelength, H, which is Planck's constant, times C, all this divided by lambda. Okay, equals, so we'll punch in 6.626 times 10 to the -34 joules times a second, because that's the units of Planck's constant. So make sure you have that memorized, or it's written down somewhere in your notes to use in class, times the speed of light, which is 3.00 times 10 to the 8th meters per divided by, and what is the wavelength in problem B? It's 52 nanometers. So when we write 52 nanometers, remember the units of wavelength needs to be in just meters. So we're going to substitute out this right here with times 10 to the -9. That way we will instantly get meters, because that's what the prefix nano means in powers of 10. So 52 times 10 to the -9 meters. I know this is not written in scientific notation, but that's fine. It is only being used in computational purposes. It's not written as a final answer. So, but it does allow us to be able to punch it into the calculator now. So let's punch this one into the calculator. All right. So we have. Let's see what we've got here. We're going to punch it all back in. 6.626 times 10 to the -34 times the speed of light, 3.00 times 10 to the 8th, but we have just 52. Okay, so notice that I was lazy. I just told my calculator to go back and I just changed it. But see, there's the top numbers, 6.626 times 10 to the -34 times 3.00 times 10 to the 8th divided by 52 times 10 to the -9, because that was nano, because that was 52 nanometers. So 52 times 10 to the -9. Okay, I'm ready to hit equals, and I get that, and that number is correct. So let's write it down. That gives me, let's see, there's my mouse back. That gives me energy of this photon equals 3 point, I just need 2 sig figs, because 52 is just 2 sig figs, right? So yeah, just 52, so I only need 2 sig figs. So 3.8 times 10 to the -18, and its energy, so it should be what units? Joules. Alright, so I'm done with this calculation now. Now, let's look at part C. Part C is going to be the fun part. It's been a while since I've had to actually calculate the maximum kinetic energy from binding energies. So let's see here. To do this problem, we've got to know quite a bit of stuff. So let me show you the formula that we're going to be using. We know this. Okay, we know that we have the formula of basically the difference of the energies that we're going to be talking about here is equal to H times V, but that's also equal to what is it? Let me think. Kinetic energy plus W, and W is the bonding energy. Okay. Now, that formula we have to know for sure. So basically, what we're going to use is only this part of it right here. Okay. But we need to know that formula, and we need to also know that one electron volt is equal to 1.602 times 10 to the -19 joules. Okay, that we have to know for sure. So now they ask us to calculate the kinetic energy. So what we're going to do is we're going to solve this for KE. So the kinetic energy is going to equal our H times V minus our binding energy. So all I did was I subtracted W from this side and moved it to the other side. So I subtracted W from both sides. So we're going to be using this, and we're going to be using this. Okay. Now, let's go back up here and look. They tell us that we're going to do this for ejected by the photon in part B, so we're going to be using part B's answer, which is this. We'll be using this. So let me put a green star by it, that way I can remember. We're going to be using this, which is going to be our H times V part, and then we're going to do this binding energy. And they told us the binding energy was 3.7 electron volts. So we're going to do some dimensional analysis first, because we need to convert 3.7 electron volts into energy, and we're going to do that with this conversion factor here. Okay, so let's go ahead and set that up. I need to zoom out a little bit so I can get a little more work area for myself. So just be patient with me and stuff. Okay. Alright, I think that should be enough work area to get this problem finished out. Alright, so let's go ahead and do that. Now they gave us, in the problem, they gave us 3.7. Whoops. Wow, that was cool, wasn't it? They gave us 3.7 electron volts, right? Well, looking back, it says 3.7 electron volts. So yes, let's convert that. Okay. So we have 3.7 electron volts that we need to convert it into energy. We'll put that over 1. And then in 1 electron volt, there is 1.602 times 10 to the negative 19 joules. Alright, that's going to allow me to convert that. So we need to write that number down now. So that gives us let me erase this, 3.7 times 1.602 times 10 to the negative 19. And that's it. So equals, and there's that number. And I'm going to write it all down because I don't have my final answer just yet. So that gives me 5.9274 times 10 to the negative 19. Alright. Ooh, that's ugly penmanship, isn't it? Sorry, folks. Oops. To the negative 19. Ain't that what it was? Oops. Oh, I erased some of it. Times 10. 3.7 times 10 to the negative 19. Yeah, that's 5.9274 times 10 to the negative 19. Alright. To the negative 19. Alright. Now, units is joules. So we need to put that up into this equation. So the kinetic energy then, whoa, about to start out with E again. The kinetic energy, which is EK, I should start with E. EK, the kinetic energy, is equal to the H times V, which H times V is the 3.8 that I have right there. The 3.8 times 10 to the negative 18 joules minus my binding energy, which is 5.9274 times 10 to the negative 19. I need to subtract these two numbers. Alright, when I subtract these two numbers, I get 3.8 times 10 to the negative 18 minus 5.9274 times 10 to the negative 19 equals, I get 3.2. Yeah, it should just be 2 sig figs behind it because this number is the larger number than this, and it's got two numbers in the front, because if you made both of them the same size, then that would be right there, and they both have to have at least one number behind the decimal. So, because this moved forward, this would become negative 18, so it would be 0.59, and that's 3.8. So yeah, it would be 3.2, so 2 sig figs here. So our answer would be 3.2 times 10 to the negative 18 joules. Now, if you're wondering how I did get that, I'll show you. If you try to subtract these, 3.8 times 10 to the 18th, before you can subtract them, they both need to be times 10 to the 18th. And the only way that you can is if you move the decimal forward on the 5.9. That way you get 5.9 times 10 to the negative 18. So notice that in the rules of subtraction, you keep the weakest column, and the tenths place would be our weakest column because it's the largest of the weakest columns. There'll be that one and there'll be that one. So yeah, that's why we keep 2 sig figs, because that gives us 2 right there. So anyway, guys, I hope this was helpful. I didn't mean to ramble so much, but watch it again and go slow if you need to, and let me know if it was helpful. If not, inbox me. All right, guys, have a good one.